I'm bored.
What are you doing?
Sudoku.
Oh, I'm actually using an SMT solver to solve a Sudoku problem right now.
That's interesting. So, like you're writing a bunch of logic formulas?
No, actually not. I'm using your favorite programming language, Python.
Ah, that sounds fun. But for that, you probably had to install some libraries and take care of dependencies and all that.
No, I'm actually using cvc5 in Google Colab. Let me show you.
Okay.
So I don't need to install anything. This is a Python notebook, and I just run pip install cvc5, and then we're good to go.
Oh, but I thought we don't need to install anything.
So this installs cvc5 on the server, so you don't have to install it on your local machine.
Ah, cool. And like it's everything online.
Yes. So we just have to import cvc5's Python API, which we do by saying cvc5 Pythonic here.
Mhm.
And then we can make our first solver object.
Okay, great. So we have a Python solver object, and I guess to model the Sudoku problem, the first thing we need is variables. So in a Sudoku, you have a 9 by 9 grid with coordinates. So for each cell, we need an integer variable, right?
Yes, but that's easy to do. So first we make this list of coordinates here. And as you said, we have 9 cells in a row and 9 cells in a column. And with that, we can then make our grid, and we will make some integer variables. So int here is part of the Python API of cvc5, and we will name them cell, and then first their row coordinate, and then their column coordinate. And I can print that, and let's see what the content of grid is for row 1 and column 2. And the name here will be cell 1, 2.
Nice. So we actually have a dictionary from coordinates, like pairs of numbers, to actual variables. And these variables have like nice names.
Yes, exactly.
Okay, cool. So having integers, variables, of course, that's not enough. We need some constraints. Like the first one that comes to mind is that each of these, the values of each of these variables have to be between 1 and 9.
Yes, that's a good point. So we can add constraints using the add function of our solver object, which will add new assertions to the SMTLib problem. So in this case, we want to say that for each pair of coordinates, the corresponding cell in the grid has to have a value greater than 0 and smaller than 10.
Wait a second, this looks like Python. It doesn't look anything like SMTlib or logic or anything.
It is. So if I actually print out the assertion, the set of assertions the solver has, we can see that this was automatically translated into SMTlib syntax. So here now we have an SMTlib and we're also using these names we gave the cells. So in this case, this assertion says that the cell in the first row in the sixth position has to have a value bigger than 0 and smaller than 10.
That's really cool. So I'm writing Python and it automatically gets translated to logic.
Yes.
Okay, great. So we have these constraints set up. Now we also need to make sure that there are no duplicates in any row, no duplicates in any column, and also no duplicates in any block.
Yes, so we also use the solver.add function for that. For the row constraint, for example, what we can do is we fix the row I, and then we have two counters, j and k, and we say that all the cells in that row have to have different values, and we of course have to make sure that j and k are not the same, because otherwise we would have said that a cell cannot have the same value as the same cell.
Yeah. What about columns and blocks?
So the column constraint is extremely similar. The block constraint is a little more complicated, but it's basically written in the same fashion.
Okay, yeah, I can see that how this can be done basically. Okay, great. So I think we covered everything. Let's check what's the solution.
Awesome. So what we can do now is to call the check method on our solver object. And if the result is satisfiable, we can also get a model that we here call M, and then I'm printing out the model. And here you can see the solution to your Sudoku.
Nice. So not only it says that the problem is satisfiable, but it also actually gives me the concrete values for each of the variables. That's great, but maybe you can do some magic and present it as a Sudoku grid.
Yes, so I've written this function here that just goes through the grid and prints it in a more graphical form so that it looks more like the Sudoku on your phone.
Mhm.
And if we print that, this is the result.
Okay, so I can clearly see that this is a valid Sudoku grid, but it doesn't look anything like the original problem I had on my phone.
Oh, of course. Yes. We never told cvc5 that there are some values already set in the Sudoku. Of
Aha.
course, then it cannot actually find the solution that you want to.
Okay, so maybe we need some more constraints that fix some of these cells to the initial values. Maybe you can set it up.
Yes, let me have a look at this. Oh, how interesting. Coincidentally, that's exactly the same Sudoku that I already encoded here. So
Cool.
basically, as you can see here in the fifth row, the second cell has value 4. So I made this initial grid here, and then I used this over add function to make sure that the cell has to be assigned that value.
Okay, great. So now let's check it.
Okay, so we run it again, and then we print the model that we get, and this is the new result.
Yeah, let's have a look. So it looks okay. It's a valid solution and it has my initial value. So you actually solved my Sudoku for me. That's great. Now I'm wondering if we have all of this set up automatically, can we find another solution? Like maybe a solution that is different on the first row?
Yes, so this is actually something really cool here. We can just add another assertion, and since we got the model back as a Python object, we can just use it. I'm sorry, I just changed something here. Let me change it back. We can just use m and access the value in our old model and say that we want to find a solution where these are not equal. And when I run the solver and print the result, we can see here that here this value has changed from a 5 to a 7.
Oh, wow, that's great. So we did find a solution that flipped 5 and 7, and that means that I can actually use the model values in new constraints. This is very strong. I can even imagine myself putting it in a loop to go over several solutions. That's great. Thank you, Hannah. I'm not bored anymore.
Awesome.